All right. So yes. So I'm Stephanie Douglas on Twitter at Stephanie Douglas, and I'm going to talk about a programming lesson that I designed and taught with Emily Rice of CUNY and the American Museum of Natural History, and with Andrea Derdzinski, another Columbia graduate student. And we developed this lesson as part of the Institute for Scientist and Engineer Educators Professional Development Program, which there's a link in the Google Doc, and it's a great program that talks about designing these inquiry-based lessons. And I was supported by their NSF grant. So my first question, and thank you, Matt, for volunteering to be scribe, is a question for you all. So that's my question is, what makes good code? What are good programming practices? Good morning. Yeah.
Documentation.
Documentation. Okay.
Write your tests first.
Testing first. That's a good one.
Comments. I mean, it goes with documentation, but comments.
Yeah. So comments and documentation. Other thoughts? Kelly.
Code, like decipherable code, like even though something could be written in one line, you don't necessarily do it because it would be indecipherable.
Okay. Readable code.
Good variable names.
Good variable names.
Read the maintenance code guide and then follow it.
Read the what? Sorry.
There is a document called maintenance code guide.
Yeah.
So read that and follow it.
Okay. So read style guides.
Don't be clever.
Don't be clever. Okay.
Know what your user base wants.
Know what your user base wants. Okay, one more.
Have someone who is not you review your code.
Okay, pair coding and sharing code. So please add to the Google Doc if you have other things, because I do want to know. But now my question is, how often are these taught in astronomy-based Python classes and tutorials?
Never.
Okay.
Almost never.
So my point is to remind people of this fact and maybe to talk about when we can do this. So this particular XKCD comic made the rounds on astronomy Twitter right after it came out, with a lot of complaints about how quite accurate it can be about astronomer coding. And for the reason that most of us are self-taught, right? Although my favorite thing is that the mouse over text says, "I didn't even know you could use emoji as variable names." And Python has now made this comic come true. So you can use crying emoji as variable names. And so we know that these good coding practices are something that needs to be taught. But the question is how. And so I will argue that it's the same way that we should be learning how to be good scientists in general, which is getting our hands dirty, getting in there and seeing what works and what doesn't. And that I think the best thing we can do as we're teaching students and new programmers how to code is to give them a safe opportunity to write terrible code, and then help them, encourage them in a direction to see how they can write more useful code, to see what works both to make their own programs better, and if they're looking at someone else's code, to see how you can write better code for the community. I'm also not going to pretend that I have this all laid out. I'm going to talk about one lesson that that we helped design that tried to do this, and I think it's a good idea that is really applicable to this, but it's definitely something that needs some more iteration. And so the fundamental concept behind the lesson that we designed is something called inquiry. This is one of the core philosophies of this professional development program that we did. And sort of three of the core concepts of inquiry are ownership. This is the biggest one. You design an investigative lesson where the learners are driving their own investigation. So you give them a problem, and there are many ways to go about solving it, and they get to choose what they're doing and sort of discover the idea as they go through, so that they can really feel like they've discovered it and claim it. That it's also authentic, that it reflects challenges that are faced by real scientists, and so merging science concepts and practices, which I'll get to in a second. And also, one of the important things is that giving students the opportunity to reason through their choices and present the evidence that supports their conclusions. And so coming back to this idea of authenticity and linking science content with practice, The lesson that we designed was framed around a content goal that was more statistics than physics in the end, error analysis and understanding how uncertainties affect your results. And our practice goal was designing and carrying out an investigation using Python. And so this is where we're headed. And then the next thing that we did is to break these goals down into different aspects. So it's not some broad, did they get this broad nebulous concept, but what does it really look like when students are investigating this idea? And so we chose 3 programming practices to focus on. You could choose an infinite amount, but we had a day and a half. So we brought up defining chunks of code. We tried to avoid jargon, so we didn't use modules or functions or anything, but just pieces of code. Identifying and defining good variables, and planning code. Specifically, we talked about input and output of variables and files. And so, like Leah, this is intended to be a little bit of there's more here than I expect you to read, but it's in the Google Doc. So the first thing we defined is, what does it look like if students don't understand or are not getting this concept? This was something we struggled with a lot, because it's very easy to say, well, if they're not identifying good variables, you're just saying, here's the good thing, and they're not doing it. But instead of saying in a definitive way, what does it look like when students are struggling? In this case, for example, in defining chunks of code, the sort of stereotypical monolithic, just a wall of text where you've copy and pasted things over and over again and changed your numbers, would be an evidence that students are struggling to define chunks of code or reusable functions. And then, of course, we also define what does it look like when they've got it. So we can say, or students can look at this. We didn't actually hand our rubric out, but you could envision it. What does it look like when you're understanding, when you're getting this concept? So in this case, it would be that you have independent code chunks that are reusable and have good documentation. Although that's blending a couple of practices there. And so the lesson that, don't quit. Oh, jeez. Hang on, apologies. So the lesson that we designed, we actually did use real astronomical data sets as our core, but even though we weren't aiming at an astronomical topic, we gave them real data sets and then talked them through sort of the basic physical concepts behind them. Let's go to the PDF. Talking through the physical concepts behind them, the idea was that in each of these cases you could fit a line to the data. So we had crater sizes and uncertainties in those sizes from the moon. We had supernova type 1a distances and velocities, and the periods and semi-major axes of stars orbiting in the galactic center. So for the supernovae and the galactic center stars, you can probably envision what straight line we were hoping that they would fit to their data. For crater counts, it turns out that if you look at the crater density as a function of size in a histogram, it actually tells you something about the time that the surface was last had a resurfacing event. So, for example, being covered by lava, as this mare on the moon have been. And so the data set that I was supervising groups with was this cratering data set. I should mention we had astronomy and geology students in this activity. And so it was a bunch of crater sizes, which I had already binned for them and wanted them to fit a line too, but they actually decided that they wanted to play with the data themselves. So one of the interesting things about this method of teaching is that the students can veer off in some interesting directions, and if they veer like into totally left field, you can kind of nudge them back, but one of the powerful things is that they can play with the data, and they actually did come up, they actually did a pretty good job playing around with histograms. And so the prompt for the activity that we gave them was just, here's your data, ask a question, and then in the end, you should have a plot that you can explain that shows your data, the uncertainty on it, your result, and the uncertainty on your result. And so then we just let them go for 3 hours. And we sort of hovered around, but for the most part, they were the ones doing the coding and asking questions with the data, and we would sort of nudge them in the right direction. So for example, so this is just a histogram showing crater frequency as a function of diameter. This one was actually an example of where the facilitation is really important. So I walked up behind this group, and they had copy and pasted this little snippet that said where craters are in between this size and this size, count the number. And then they copied and pasted it and changed the numbers and did that 19 times. And so then what the role of the facilitator then is to say, so that looks like a lot of work and taking up a lot of space. How can you make that more efficient? They'd had a small Python lesson before the activity. So what do you know about Python that could make that more efficient? With the goal of having them put that into a loop. Although then they actually, in doing their research, found the NumPy histogram function, which reading documentation and finding pre-made things is also an important part of learning how to code. So then the other group said, great, we made a histogram. And so the question then is, okay, how can you go, what's the next step? You've counted just the sizes that I've given you, but what about when, how does the uncertainty on the sizes affect it? And perhaps one of the practices we also should have talked about might have been plot design, but we weren't there yet. It was probably a good one. And so we had hoped they would do some kind of resampling, but in the end, they subtracted all the uncertainties and got lower limits on the sizes, added all the uncertainties and got upper limits. And so the green is sort of this lower limit histogram, and the blue is the upper limit histogram. So in the end, and that brings me to one of my other points. In the end, the students didn't necessarily get all of the things that we told them about, that we wanted them to. But the point is that they came out of it really excited and confident in the fact that they could program and they could think about uncertainties. And that, I would argue, hang on, I'll do this in a different order. That, I would argue, is almost more important than that they get everything exactly right. If they get most of the way there, you can kind of later on, after the fact, say, okay, here's maybe the rule that we were trying to get you to follow. But especially, I think, in Astro programming, where a lot of people, especially new learners, can feel intimidated, giving them the opportunity to feel like they've discovered something about coding and that they've really written their own code and tried and errored and gotten something to work, I think is extremely important as we're teaching coding. And one other thing I wanted to mention that was the previous slide, we actually, so this was not taught in a class, we were teaching summer research students, and so we actually had no incentive to keep track of their progress, and so we got to the end and sort of had a general sense that they had, the students had sort of progressed forward in all of our coding categories, but we actually had no way of quantifying and showing the differences, which I think we would do differently in the future to show. So for example, I don't have that 19 copy and pasted plan for making a histogram. And like I said, we did this as part of the IC professional development program. And so I talked about the inquiry aspect of this. They also, a lot of the workshop focuses on equity and inclusion and designing assessments. This year's, the 2016 workshop started last week, but their application deadline is in December, and I highly suggest that people sign up for that. It was a really great experience, and I learned a lot. So I think we should be teaching programming practices, and we should be doing it with, at least sometimes, these inquiry-style lessons that give students the chance to really act like scientists and scientific coders and gain more confidence in their programming skills. And I also want to do a sprint either today or tomorrow on this, because planning this does take a lot of time. There's not so much we can do about the facilitation time investment, but I'd like to see if we could get some of these programming practices and or inquiry-based lessons out into the community. So, thank you.
There seems to be some overlap with software carpentry. Can you talk about why you didn't decide to piggyback on that?
In our case, it was because we had to design the lesson from scratch. But yeah, that is probably a good place to go to start incorporating designs, yeah. The goal for sort of the larger generating community, like a community repository of lessons, would not necessarily be to create everything from scratch. But in our case, that was part of the program.
What's the scale how many instructors did you have to how many students?
So we had 3 to about 18. So it gets, and I know that they were at the PDP, they were talking about how you can make this scale to bigger groups. But yeah, it is a challenge when you get up to larger groups. You'd have to start making more materials available for students to sort of check their own understanding, rather than being able to look over their shoulder as much. So yeah, it is more suited to sort of smaller groups. But I think the other thing I think is for the things that will help a larger classroom set will be some of the same things that will help looking at like an online tutorial or again, going back to where people still are self-taught. I think the same sort of rubrics and material will help in both cases.
Do you have a sense for how to get students who are reluctant to get their hands dirty more excited about exploring and doing their own programs?
So I think I don't know if this is a cop-out answer or not. I think the best way to do it is to at least once give them, like, build up the kind of environment where they can make the mistakes. So one of the things that we started them off doing to kind of get them in the sense of just throwing things out there is that we had stations for each data set, and we said, we want you to ask a question about uncertainties. This wasn't necessarily programming, but like, just brainstorm as many ideas as you can. Don't worry about whether they're like right or the best idea. Just there are like activities out there that trying to get students to not try to come up with the best idea first and generate. Is that?
Did you have a wide range in like prior knowledge and experience with your students, and how did you handle that?
So for the most part, they were mostly beginners. So most of them had like a week-long Python tutorial the week before. So that's one of the reasons we could focus on practices and not just programming. But for the most part, they were mostly inexperienced coders, and like the geology RU students they in particular had a challenging time. So with them, we focused more on the code design than necessarily the Python syntax itself. And so it's another thing where you need a small class, being able to sense who's struggling more and who you can challenge a little bit more in terms of coding syntax itself.
One more question.
I'm curious about how you grouped, how to ask this. You were a bunch of kids at one computer? Did you have multiple people working on different computers at the same time? And do you have a recommendation for how to do that?
So we had groups of 3, ideally sharing one computer. That worked in some cases where students were really good about keyboard sharing and getting to something akin to pair programming. We also had groups where somebody dominated the keyboard, or somebody would just took their own laptop out and started tapping out their own ideas and not contributing. And so for the most part, what we could do there is just sort of try to encourage them back into the group. But yeah, that was actually one of the challenges that we faced. But we regrouped them in 3s.
We did have one more question.
So I guess the one thing I wanted to say was, and this showed up a couple of times in what the students did, one thing none of us said, which you should say first, is when the first step of good coding practice is to think.
Yeah.
And so clearly some of the students went and read the documentation and figured out how to do something, as opposed to just blindly throwing some code at it.
We did make them plan actually before we let them. Yeah, I should have mentioned that. We gave them big sheets of paper and tried to get them to do some pseudocoding and flowcharting before we got in there. That was why one of the aspects was planning input and output and not just jumping into code. But yeah, you're right. I didn't put that in there. So.
All right, let's thank Stephanie again.